So today we're going to be looking at a new topic which is called agitation equipment and impeller. So many processing operations depends for their success on the effective agitation and mixing of fluid. So first of all, let us look at the definition of mixing and agitation, how they are different and how they are related. So first of all, mixing can be defined as the random distribution of two or more initially separated phases. So for example, the easiest example that we can take is like, let's say you have a glass of water and you want to mix it, you want to add sugar in it. So initially your water is a separate phase and the sugar is a separate phase. So by mixing it together, you are creating a random distribution between the water and the sugar. So next thing that we have to look at is the agitation. Agitation is defined as an induced motion of material in a specific way. So remember, when you want to mix something, you have to have a motion of mixing. So usually in our case, between water and sugar, you usually use a spoon. So your spoon can be classified as agitator. So the motion that is created by the spoon, it's called agitation. So that is why agitation is required for a mixing. If there is no agitation, there will not be any mixing. And the pattern is usually normally circulatory and normally taken place inside a container. So that is how mixing and agitation can be related. So let us look at a video of how mixing can happen. So this process is happening in a laminar flow with high viscosity fluid. So in this, the high viscosity fluid is the corn syrup and we are mixing it with water. So initially in this tank you will have a corn syrup. So this is the first phase and then you are adding water, which is the second phase. So with the help of this agitator, which is mounted to a shaft, and here you have type of impeller, so you will mix the two separate phases together. So you can see that initially there were two separate phases. After a while, by the help of the agitation, the two phases are mixed together. So liquids are agitated for several purposes, such as the first one is suspending solid particle. If you have solid particle in a liquid, so if you want to suspend it, you use the mixing process. The second one is blending miscible liquid. For example, you want to mix alcohol and water. The third one is dispersing gas through liquid in the form of small bubbles. And the fourth one is promoting heat transfer between liquid and a coil or jacket. So let us look at another video of mixing. So in this mixing, we are actually using double pitch flow impeller. So in this process, we are going to be looking at the addition of dye into a water solution. So initially you have your solution. So you can see here we have two impeller mounted. So if you want to have a better mixing, it is sometimes necessary to have two impeller. So when we are adding dye, it helps visualize the blending process with the fluid. So you can see initially it was colorless. After you add the dye solution, it it turns the solution into a homogeneous color. So you can see here, this is what we mean by the random distribution of two initially separate phases. And you can see here the blend time is relatively short. So this is the top view of our container that we are using for mixing. So liquids are usually agitated in a tank. So this is a diagram showing a tank for mixing. At the bottom of the tank is rounded. So you can see here, usually most of our mixing tank will have a bottom rounded. Impeller creates a flow pattern. So this is what we call an impeller. So impeller will be fixed on a shaft, and a shaft will be mounted on a motor. So the combination of motor, impeller and shaft is known as an agitator. So you will have, if let's say we say what is an agitator, agitator consists of a motor, a shaft and an impeller. So the motor will be operated uh, by sending electricity through it. So once the motor is spinning, it will cause the shaft to spin and it will cause the impeller to spin as well. And the motion of that created by the impeller will cause the mixing process. So small scale tanks are constructed usually in Pyrex glass. So the material that we use is depends on the volume of our mixing tank. For large reactor or tank, stainless steel is usually used. Speed reduction devices are used to control the agitation speed. So you can see here, by having a speed reducer, we can actually control how fast we want our mixing process to be. So when we are talking about mixing, we will be mentioning the type of flow in mixing. So we can have three type of flow patterns, which are axial, radial and tangential flow. So these three main types. So in order for us to have these three type of flow, we will use what we call an impeller. So three main types of impeller for low to moderate viscosity liquids are known as propeller, turbine and high efficiency impellers. So impeller here is the general term. Propeller, turbine and high efficiency impeller are the specific types of impeller. So first of all, let us look at the types of impeller that we have. The first one is a propeller. Propeller is a type of impeller that is used to create an axial flow. So remember we said that we have three types of flow. So if you want to create a flow pattern which is axial flow, we'll use propeller. So flow currents is pushed downwards in the downward direction parallel to the shaft. So remember, this is your shaft. So once this is spinning, it will create a flow in this pattern. So first of all, your mixture or solution will come, the flow will come down and then go up, come down and go up. So this is what it means, that the flow pattern is parallel to the shaft. It is usually used for high speed for low viscosity liquid, and it is effective for a very large tank. It is suitable for mixing of low viscous liquid and particle suspension. So in a deep tank, 2 or more propellers might be mounted on the shim shaft. So as we saw in the dye mixing example, you had 2 propeller mounted on the same shaft. So this is required based on the depth of our tank. The second one is turbine. Turbine is defined as multi-bladed pedal agitator with short blades. The diameter is usually around 30 to 50% of the vessel diameter. It is suitable for a wide range of viscosity. So for low viscosity, it generates strong currents which continue throughout the vessel, and the principal current produced when you are using turbine is radial and tangential. So for propeller, it's focused on axial flow, whereas for turbine, it will produce radial and tangential flow. So these are some examples of turbine that we can use in our tank. So we can have straight blade turbine, disc turbine, pitch blade turbine, and concave blade disc turbine. The next one is we're going to be looking at high efficiency impeller. So this is a variation of the pitch blade impeller, developed to provide more uniform axial flow, better mixing, and to reduce the power requirement. So the power requirement we'll be looking at in our next class. Widely used to mix low and moderate viscosity liquid, not recommended for very viscous liquid or for dispersing gas. Impeller has a 3 slanted blades that are cranked to decrease the blade angle at the tip. So these are the types of high efficiency impeller. Now we're going to be looking at the type of flow that we can have in our mixing tank. The first one is the axial flow. So as we mentioned in our propeller, so axial flow is created when the impeller makes an angle less than 90 degrees with the plane of rotation, thus creating flow patterns toward the base of the tank. So again, the direction of flow is parallel to the shaft. The flow will go down and then will go up. More energy efficient than radial flow. More effective in lifting solids from the base of the tank, and is usually used for blending and solid suspension. So this is a video to show how does axial flow look like, the axial flow pattern. So we are using impeller diameter 1/3 of the tank, and then we are using colored beads. So this is the modeling on how axial flow will look like. So you can see here we are using propeller that is mounted to the shaft, and we have your colored beads that are moving down and going up, moving down and going up. So you can see that the flow is parallel to the shaft. So if you focus on one bead, you can see that the bead is going down and moving up. So this is how we classify this as an axial flow. Next, we'll be looking at radial flow. So radial flow is a flow that acts in a direction perpendicular to the shaft of the impeller. So let's say this is the shaft of the impeller. This is your impeller. So usually we'll be using turbines to create radial flow. So the direction is perpendicular. So this is the shaft and this is the directions. So the currents travel outwards to the wall vessel, then either upwards or downwards. So it will go outwards and then it will go upwards or downwards. It requires higher energy as compared to the axial flow impeller and is usually used for dispersion. So again, a video to actually visualize how does a radial flow looks like. So again, we are going to be using impeller diameter 1/3 of the tank diameter, and we are going to be using the same colored beads. So this is how radial flow will look like if we model it. So this is the shaft and this is the turbine that we are using to create a radial flow. So you can see here the beads are going outwards and then upwards or downwards. So this is a clear illustration of how a radial flow will look like. Next, we're going to be looking at swirling flow or vortex formation. So this is also what we call tangential formation. So it acts in a direction tangent to the circular. So you can see here, this is what we mean by direction tangent to the circular. At high impeller speed, vortex is formed and may be so deep that it reaches the impeller. So this is an example of, this is the shaft, this is the impeller, and this is what we call a vortex. So you can see here, if it's the speed is very high, it can reach up to the impeller. The higher the speed, the deeper the vortex. So what can it cause? It can cause power absorbed by the liquid is limited, effective volume reduced, and mixing effect is worsened. So if our vessel has a vortex, the mixing will not be good and the power we are using will be increased. If the solid particle present within the tank, it tends to throw the particle toward the outside by centrifugal force. So if let's say you have a particle here, so it will not be mixed, but instead it will be thrown and will be deposited on the wall. So vortex formation is undesirable and we want to prevent it as much as possible. So here we'll look at how does a vortex is formed. So here we are causing vortex, and the vortex is formed because we are using two separate and different type of impeller. So you can see here, this is how a vortex is formed. And if you increase the speed, the vortex formation will be higher until it can reach the impeller. So if you have vortex formation, the mixing will not be good, and then we are wasting our power instead of mixing our phases. So in order to avoid the formation of vortex can be prevented by having a few different ways. So the first one is we can mount the impeller away from the center of the vessel, or the impeller is tilted in a direction perpendicular to the direction of the flow. So let's say this is the top view of your mixing tank. This is the center line. So instead of mounting your impeller shaft in the middle, you mount it offset, off center of the vessel. So this is the side view, so it look like something like this. So instead of having your the impeller shaft over here, you have it offset to the left or to the right, depending on your process. So by having this, you are actually able to prevent the formation of vortex. The second one is that the impeller shaft is tilted at the angle. So instead of having a straight center, you tilt it at the angle, and by having this, you can prevent the formation of vortex. So this is an image of how the flow pattern looks like if the first one is that the propeller is mounted offset from the center line, not in the center, and then this is how it looks like if it is tilted at an angle. So you can see here the mixing is better as compared to the center mounted. So this is actually a video that illustrates how we can have. So the first one is offset mounted agitator in an unbaffled tank. So again, the impeller diameter is 1/3 of the tank diameter. It is operating colored pellets with specific gravity slightly having water are added to represent suspension of solid. So you can see here, this is offset mounted agitator in an unbaffled tank. So if you, by having the offset, you can see that the mixing is quite good. So it will create less vortex, and there is better top to bottom liquid flow pattern. So the second way to prevent the formation of vortex is by having baffles on the tank. So baffles are vertical plates perpendicular to the tank wall. It is suitable for large tank with vertical agitators. So this is a side view of how your tank with baffles will look like. So again, this is your shaft, this is your propeller, and you add perpendicular plates into the tank. Propeller drives the liquid down to the bottom of the tank, where the stream spreads in all directions towards the wall, flow upwards along the wall, and return to the propeller suction from the top. So this is how a very large vessel will look like without any baffles. You can see here, because of the formation of vortex, the solid is actually on the bottom and there is poor distribution of the solid. So if we add the baffles here, you can see that standard baffling parameter promotes flow that results in good solid distribution. So you can see here the difference between without baffle and having baffles. So let us look at a video that shows the effect of having baffles. So centered mounted agitator in a baffled tank. Again, the same thing, we are using impeller is 1/3 of the tank diameter. So you can see here, these are the baffles that were added in the tank. So by having the baffles, the flow, the beads are actually going down and going up, and then because of the addition of baffle, it will prevent the formation of vortex and the mixing will be even better. So you can see here, unlike the unbaffled tank, there is no center vortex and there is a good top to bottom circulation of particle. So that is all for our class for today. In the next class, we'll be looking at power number and how to actually calculate power, because as we mentioned before, it is important for us to have a very good mixing so that the efficiency of the power we are using is good. So in the next class, we'll be looking at what does power number means and how do we calculate the number.